Hello everyone, I am Engineer Adam C. Abinales. Today, I am presenting you a video on outstanding buildings. These buildings were awarded and recognized by the International Association of Bridge and Structural Engineering, or IABSE. This video presentation of standing buildings is published here in the Aztec YouTube channel, and we invite everyone to subscribe. In the year 2011, the Outstanding Structure Award was given to Burj Khalifa Tower in Dubai, UAE. The tower itself, an aesthetically striking super tall building that utilizes a Y-shaped, buttressed concrete core and steps spiraling vertical shape to address never before seen structural requirements and achieve a record-setting height. The tower height at 828 meters makes the Burj Khalifa Tower as the world's tallest structure. To achieve this record-setting height, it was necessary to push the limits of current analytical, materials, and construction technology. The structural engineer of this tower was Bill Baker. The main contractor was Samsung C&T. The architects were Skidmore, Owings, and Merrill, or SOM. The total floor area of this tower is 309,473 square meters. The total number of floors is 154 plus 9 floors for maintenance. There are 57 lifts, and the structural system used in this tower consists of the reinforced concrete, steel, and aluminum. Each of the wings buttress the others via a six-sided central core or hexagonal hub. This central core provides the torsional resistance of the structure. Corridor walls extend from the central core to near the end of each wing, terminating in thickened hammerhead walls. These corridor walls and hammerhead walls behave similar to the webs and flanges of a beam to resist the wind shears and moments. Perimeter columns and flat plate floor construction complete the system. The Burj Khalifa Tower is considered a very efficient structure in that the gravity load resisting system has been utilized so as not to maximize its use in resisting lateral loads. As the building spirals in height, the wings are set back to provide many different floor plates. The setbacks are organized with the tower's grid such that the building stepping is accomplished by aligning columns above with walls below to provide a smooth load path. The tower does not contain any structural transfer. This stepping and shaping of the tower has the effect of confusing the wind. Wind vortices never get organized over the height of the building because at each new tier, the wind encounters a different building shape. In 2013, the Outstanding Structure Award was accorded to 2012 Olympic Velodrome in London, United Kingdom. The velodrome, a combination of simple technologies creatively combined and engineered to produce an elegant, innovative, and sustainable building. This structure is a world-class venue which intelligently answers questions of function, beauty, sustainability, buildability, and value. The owner of the structure is Olympic Delivery Authority. The structural design engineer was Expedition Engineering. The contractor was ISG, and the architects were Hopkins Architects. Velodrome had used 4,500 cubic meter of concrete with 800 tons of structural steel. The project was completed in February 2011. The 2012 Velodrome, with 6,000 seats, served as an Olympic and Paralympic stadium for track cycling during the 2012 Olympic Games. The 13,000 square meters roof is supported with a doubly curved cable net formed from 36 millimeter diameter cables stressed between a perimeter ring beam. The desire to reduce working at height was a significant reason for opting for a cable net roof. The cables were laid out at ground level, clamped together and safety netted. All elements above the in-situ concrete floor slab were prefabricated to improve speed, cut down on waste, and improve quality. The velodrome required a highly insulated roof, leading to the need for rigid supporting roof panels. A novel articulated roof cladding system based on prefab timber cassettes was developed, ensuring that all 1,050 cassettes had appropriate tolerances to deal with the flexing of the roof under a wide range of loadings. The Canton Tower in Guanzhou, China, was a finalist in 2014. The structural design was by Arup. The architect was information-based architecture. The construction started in November 2005 and was completed in 2010. The total building weight is 98,450 tons, and the antenna weight at the top is 1,550 tons. The total number of floors is 37 plus 2 basement floors. The total number of lifts and elevators is 9. Another finalist of OStrA in 2015 was Abeno Harukas in Japan. Abeno Harukas, or simply Harukas, is Japan's tallest skyscraper, standing at 300 meters and was completed in March 2014. Haruka's building, situated in Abeno, Osaka, is located immediately above the station and a super high-rise vertical city with a gross floor area of 212,000 square meters. Haruka's building is owned by Kintetsu Real Estate Company Limited. Its construction was completed by a consortium of Takenaka Corporation, Okumura Corporation, Obayashi Corporation, Dai Nippon Corporation, and the Senitaka Corporation. Haruka's building sits on a site area of 28,700 square meters. Please allow me to show in this slide our family photos during our trip in Japan last December 2017, in which the background is the Abeno Haruka's building. Towering above the city of Shanghai in China with 24 million people at a height of 632 meters, the Shanghai Tower was awarded as OStrA 2016. It is the tallest building in China and the second tallest in the world, only to be surpassed by the Burj Khalifa in Dubai. Shanghai Tower has 120 stories and sits on a total site area of 30,370 square meters. The gross floor area is around 573,400 square meters. The tower structure takes the form of 9 cylindrical buildings stacked one atop another, including a business zone at the bottom podium levels, 5 office zones, 2 hotel apartment zones, and sightseeing or observation decks at the top. Each zone can be considered an independent city or village with communal space at an amenity level extending to the outer twisting facade. The tower floor plate diameter varies by zone from 82.2 meters at Zone 1 to 46.5 meters at Zone 8. The stacked zone tower concept within an exterior facade tapering and twisting with height creates a spectacular architectural design. Due to its super height and the twisting and rotating facade, the wind loading is one of the controlling factors of the structural design of this tower. The wind tunnel testing proved several exterior vortex architecture. The Gentile twist is architecturally pleasing but also serves a meaningful structural purpose. The maximum wind loading forces depends on the twist of the tower. The wind tunnel test favored a 180-degree twist. However, aesthetic concerns prevented a full half-turn in the final design. Instead, a 120-degree vortex was considered the best alternative. The 120-degree design provided benefits as it saved up to 24% in the necessary structural wind loading design work and construction materials, and this amounted to 50 million in savings. Sway is a common problem among many skyscrapers, and windy conditions can cause occupants to feel nauseous from the building movement. With a tune-mass damper near the top level, Shanghai Tower should not have this problem. A computerized stabilization system controls pistons that push the 1,200-ton mass into the leading phase of the wind force. This large movable mass at the top of the building reduces the potential for sway and allows occupants to remain comfortable inside. Last but not the least, in this presentation is OStrA 2017 Phoenix Center in China. Phoenix Center represents a complex spatial structure originated from three-dimensional parametric design techniques resulting in an extraordinary interaction of architectural and structural aspects. Phoenix Center is owned by Phoenix Satellite Television Company Limited. The structural engineers were Zhu Wenong, Zhu Zongyi, Zhou Zihong, Zhang Zhisong, Shen Zhenkai, Wang Yi, Bulong Yi. The Phoenix Center sits on a site area of 1.8 hectares. This 2017 OStrA is located next to the southwest corner of Chaoyang Park in Beijing. The site, as earlier mentioned, 18,000 square meters, with a construction gross floor area of about 72,000 square meters, and the building height is 54 meters. Using accurate 3D digital modeling techniques, the structures, especially the curtain wall supporting system, create enough spaces for different architectural functions and also contributes to the aesthetics effects of the entire building. Elevation difference between the southern and northern internal spaces are able to provide quality of sunlight, ventilation, and landscape view to the office towers, meanwhile avoiding glare and noises from the broadcasting room. In addition, the elevation difference also avoids blocking the sunshine to the residential building at the northern direction. The cone-shaped shared space, which is 30 meters in height, generates the chimney effect, which provides natural air ventilation to save energy during transitional seasons. Okay, this is the end of my video presentation, and hope you enjoy this video. And watch out for our next episode in this Aztec YouTube channel. Have a great day, everyone. See you.